So one of the most important things that we'll do in this chapter is attempt to find the rate of a chemical reaction. And I really want to take a pause right here and to make a little note that these are typically only found experimentally. Now, we'll be getting into what that experiment looks like and how to manipulate that data in another lesson. But for today, I really want to talk about something called a one-step mechanism and something called a rate law. And sometimes that's called a rate law expression. So let's start with this, a rate law expression. A rate law expression is simply an equation that can be used to find the rate of that chemical reaction. And honestly, because all of the materials generally have only the reactants in common, you'll typically find the quantity of those reactants on the inside of those reactions. I'm going to show you how to do this in just a second, but I want to explain what this one-step mechanism thing is all about before we do this. Now, what we're about to talk about is only valid for something called a one-step mechanism. So a one-step mechanism is a reaction that occurs exactly as written. There's no side reactions. It happens in one step. So in other words, we are not talking about Hess's law here. Now, in thermodynamics, we did talk about that some reactions are too dangerous to actually occur in one step, so we break it down into a series of steps. Now, for kinetics, what I'm about to show you here, that scenario cannot exist. So if I said A makes B plus C, then that means that A spontaneously breaks down into B and C. It doesn't go and make D first to try and make B and C. This is direct. Boom, one-stop shop, and you're done. This is what we would call a one-step mechanism. A mechanism is simply a way of explaining the how the chemical reaction takes place. So we're saying that how this reaction takes place is it happens in one step. A will decompose into B plus C. In that case, the rate is actually directly proportional to only one thing, and that would be my reactant, and since I only have one reactant, boom, there it is. Now, I don't know about you, but I don't have a directly proportional to button on my calculator, so we need to change this out mathematically to something more concrete. And this is what it's going to end up looking like. I'm going to switch my directly proportional symbol out for an equal sign. But to make sure that this expression can always be true, I often have to add in a little fudge factor. And that's what this is going to be about, the factor K. Now, K is what we call our rate constant. And again, it's just a mathematical fudge factor that constantly is going to make this equation make sense and make sure that it's good to go. Very important to note that this is only good at one temperature, and that it's only good for one reaction. So no two reactions are going to have the same rate constant, and if you change the temperature, you're also going to change that rate constant. So let's really make sure that you know how to write an equation for a one-step mechanism. Let's look at a couple more examples here. Well, what if our reaction was 2A makes B plus C? So again, we'd be explaining the initial rate, and that means that only my reactants would be present. So my rate is going to be directly proportional to or equal to some fudge factor K, which we call the rate constant. And in this case, it's going to be times the concentration of A squared. So notice that the coefficient to the chemical reaction became an exponent in the overall equation for my rate law. And that's because this coefficient does have a multiplicative effect on this overall rate. Now we do have a fancy way of referring to these exponents in this chapter. We call these exponents orders. So this reaction is actually second order with respect to the concentration of A. Let's take a look at another one. What if instead I was dealing with 2A plus 5Z makes B plus C? Well, then I would write this reaction out as rate equals K times the concentration of A squared times the concentration of Z to the fifth. So everything is going to be multiplied together. There's no adding here. And the coefficients simply become the orders. Now this one is even more kind of interesting. So this reaction is second order with respect to the concentration of A. This reaction would be fifth order with respect to the concentration of Z. And overall, we can also talk about the overall order. Overall order. Now, mathematically speaking, when you multiply two numbers together that have two different subscripts, but powers, what do you do mathematically to those? We add them together. So we do the same thing mathematically to explain the overall order. So this would be seventh order overall. Now I know that the order of the chemical reaction doesn't make a lot of sense right now, but I will talk about that in a subsequent video. But for right now, again, we're writing rate law expressions, which is just a mathematical way of calculating the rate of the chemical reaction. And we're doing this for one-step mechanisms. One-step mechanisms would happen exactly as they're written on the page. This one, it would take 2 A's and 5 Z's bumping into each other to be able to make B plus C. I'll be identifying them as one-step mechanisms for you, otherwise it would be impossible to tell, which is generally speaking why the rate of a chemical reaction and a rate law expression can only be determined experimentally.